Hi, I'm Scott Burke, and I'm pleased to talk to you today about my 3-year art project/science project to create a computer from scratch out of discrete electronic components, and for extra retro computing flair, to build the hardware and software for it to communicate with my old Apple II Plus. I started this project because while I've been using computers, programming them, and even playing around with their innards for over 40 years as a hobbyist, I've had no formal computer science or electrical engineering training. I knew a lot of terms and understood a lot of the individual concepts, but had no clue what really goes on inside a CPU. Fortunately, in the internet age, there are a variety of high-quality, free educational opportunities. I found a fantastic resource over at edX in a series of courses called Computation Structures out of MIT. Through this course, I gained a great understanding of how CPUs work, and the idea to create a large visual computer began to take shape. The course taught me how transistors work to form the basis for computers by acting as an electronic switch. I learned how transistors can be put together to build all the common logic gates through circuits containing just a few components. And I learned how compositional these gates are. That is, you can combine them in various ways to make building blocks essential for computation, such as multiplexers to select and route signal paths, adders to add binary digits, and the D flip-flop, which can serve as 1 bit of CPU memory and represents a way to store state and provide registers for our nascent CPU. Armed with all that knowledge, it was time to build some stuff. Because this entire project was one big prototype, I used solderless proto boards to lay the whole thing out. That made it very easy to debug, test new designs, and even modify the CPU design along the way. I included LEDs to show the current state of the signals and registers for almost every component of the computer. Here's 3 bits of the full adder, part of the ALU. And here's 3 bits of register memory. At 60 transistors in a 6-inch by 2-inch area, this isn't exactly large-scale integration, but it's actually comparable in transistor density to some of the early integrated circuits made in the 60s. While it's beyond the scope of this talk to discuss every facet of the Spikeputor design and construction, you can find it all in the Spikeputor project page on Hackaday. I've also put a link to the project in the Discord channel. Important Spikeputor specifications are summarized here, and I'll discuss these points in the following slides, along with some photos of the real thing. The Spikeputor layout consists of a series of mounted solderless proto boards on 3 2-foot by 4-foot pegboards, conveniently making the total 8 by 4 footprint the size of one of my living room walls. I found a great Frankenstein-style switch plate on eBay and incorporated it as the on-off switch. It runs on a 5-volt power supply and consumes a maximum of 25 watts of power, adhering to the initial design to make this thing more like a light bulb rather than a hairdryer. It contains roughly 6,000 transistors. It's battery-powered, running off a rechargeable sealed lead-acid cell. In addition to the numerous LEDs, there are some hexadecimal digit display chips to read out the values of important registers and outputs. And I also installed electroluminescent wires, which are driven by CPU signals to light up the currently selected data paths, making the computation steps even easier to visualize. The pegboards themselves divide up the Spikeputor's main function. One pegboard houses all the processor registers, another the entire ALU, and the third the rest of the components. Here's a closer look at the processor register pegboard. The Spikeputor has 16-bit address and data buses, so the registers are 16 bits wide. There are 8 CPU registers. Registers 0 through 6 store actual 16-bit values, where R7 is hardwired to 0, and that can be used to quickly zero out other registers or memory. You can see that each row represents a separate register, with the high bits on the left and the low bits on the right, and this general structure is repeated throughout the Spikeputor design. The Spikeputor instruction set uses a RISC load-store architecture. In addition to memory load and store functions, the instruction set features a host of ALU commands and both conditional and non-conditional branching. This is a close-up of the ALU. It has 4 main modules to perform Boolean math, signed addition and subtraction, signed and unsigned comparisons, and variable right and left bitwise shifts. The final pegboard contains the rest of the functions of the CPU. The control logic is a collection of logic gates made up of about 80 transistors that translate Spikeputor opcodes in current CPU state into all the signals required to fetch and execute instructions. The control logic also handles incoming reset or IRQ signals. Main memory is the only functional piece of the Spikeputor where I used chips rather than discrete components, because to provide even a modest amount of discrete transistor-based memory would have been prohibitively large and prohibitively tedious. And I really wanted to use this computer to run real programs and not just some tiny few liners. Since I had a 16-bit address space, I used 64K ROM and RAM chips. There are 16 bits each of general purpose input and output, mapped to special memory locations and accessible via simple read and store CPU opcodes. Machine language instructions are composed of 16-bit words. One-word opcodes are used for operations between registers, and two-word opcodes are used for operations between registers and constants. Special registers shown on this pegboard include the instruction register, which holds the currently executing instruction, the constant register, which holds the constant operand for those two-word instructions, and the program counter, which stores and updates the address of the next instruction to be executed. The Spikeputor has a variable speed clock, which uses a discrete transistor version of the venerable 555 timer chip. A rotary knob can select the speed along a range from 0.3 Hz to 3000 Hz, and can also be switched into a single step mode, which advances the CPU one clock cycle at a time. Finally, and this is where the Apple II comes in, I designed a direct memory access capability wherein an external device can halt the Spikeputor CPU through the control bus and have full read-write access to all of its main memory, as well as a few important control signals. To enable DMA, I chose to build a Serial Peripheral Interface, or SPI, peripheral board for the Spikeputor, which could be controlled by an SPI controller board operated on external devices. The board sits next to the Spikeputor and connects directly to the Spikeputor control bus, address bus, and data in and out buses. SPI is a de facto standard for synchronous serial data communication. The SPI communications protocol consists minimally of 4 wires: a chip select signal to tell the peripheral to receive and send commands, a clock signal provided by the controller to synchronize the sending and receiving of individual bits, and 2 lines that provide input and output signals between the controller and the peripheral. This is much simpler to implement than asynchronous serial communication schemes like RS-232. The Spikeputor DMA card can handle a number of commands, each of which is either 1 or 3 bytes long. The command set, sent to the SPI peripheral input, provides operations to halt and restart the Spikeputor, to send reset or IRQ signals, and to read or write to the current address, which can either be selected by the set address command or set to be incremented automatically after each read or write via the auto increment command. The output from the SPI peripheral consists of a byte with a series of status bits, as well as the high and low bytes of the Spikeputor's current data bus. And finally, we get to the Apple, which is used for long-term storage of Spikeputor programs and to act as a smart terminal for the Spikeputor itself. To communicate with the Spikeputor SPI peripheral, I made an Apple I/O card to act as the SPI controller. Called BIOS, an acronym for Board to Interface the Apple to the Spikeputor, the card has chip select signals to control up to 4 different SPI devices individually or simultaneously. So in addition to communicating with the custom Spikeputor board, it can be used to control a variety of SPI-enabled devices, like smart LEDs, displays and sensors, as well as embedded processor platforms like Arduino or Raspberry Pi. The schematic shows how the card interfaces through the Apple's I/O system. To use Apple I/O cards, you write data to or read data from special memory locations that correspond to the slot number the card is plugged into. The card has access to the Apple's address and data bus signals, among other important ones, and can react to these reads and writes to perform the desired function. The details of the card, which includes chips for buffers, timers, decoders, latches, and shift registers, are described in a separate Hackaday project, and the link is also included in the Discord channel. It doesn't take much Apple assembly language to send and receive bytes through the SPI card. This subroutine sets the desired SPI channel, then sends 3 bytes corresponding to the Spikeputor DMA command. For each byte transfer, it sends the byte to the card, starts the SPI transfer, then polls the card to wait until the transfer is complete. Then it reads and stores the reply byte and loops back. After 3 bytes are sent and received, the chip select signals are cleared to end the SPI transaction. To actually program the Spikeputor, I wrote a simple 2-pass assembler on my Mac to convert Spikeputor assembly language to machine code. The data can be output to an SD card containing an Apple disk image via Apple Commander, and then transferred to the Apple II Plus using the floppy EMU disk emulator. On the Apple II, I wrote an uploader which transfers the machine code directly to the Spikeputor using all the hardware and software I just described, and then a monitor program which routinely halts the Spikeputor and reads and writes to predefined output and input buffers located in the Spikeputor's memory, thus facilitating two-way communication. In addition to standard ASCII characters from the Spikeputor, the monitor program can recognize predefined special characters in order to manipulate the cursor position in text mode, or set Apple II graphics modes and plot to the screen. Note that the hardware reads full 16-bit words from Spikeputor memory, so you're transferring one word at a time. So putting it all together, it's finally demo time. First, the Spikeputor is turned on and the desired program is uploaded from the Apple into Spikeputor memory. After successful upload, the monitor is run, which resets the Spikeputor and executes the newly uploaded program. After that, all of these input-output interactions are processed on the Spikeputor. The Apple is just acting like a terminal. The Spikeputor here is generating the random numbers for the color and locations of the bars, and then packaging up the predefined special character-based graphics commands and writing them to the Spikeputor output buffer. The monitor program reads the buffer when it changes and takes the appropriate actions. When the demo is complete, the monitor program can reset the Spikeputor, rerunning the program. With new input, we get a high-res demo. Note that the Spikeputor in these demos is running at about 3 kilohertz. Not that fast, and it's not going to be mining Bitcoin anytime soon, but at least fast enough to give decent real-time feedback to the user's text input. And that completes my talk for today. Thanks for listening, and please check out the references to the project and to the other resources I discussed here today. All the links have been posted into the Discord channel, and of course I'd be happy to take any questions.
Okay, thank you. Yeah, wow, amazing. We do have we about 3 minutes. So does anybody have any questions?
I've been trying to answer some of them live in the
Awesome.
Discord, and I'll go back.
Yeah, I noticed. No, which I totally get. That's awesome.
Point your monitor down.
Where are we? Where can I buy one?
Well, I probably
just popped up.
Yeah. The transistors themselves are about 10 cents each, so that's $600 or $700 right there. It's probably spent. The wires are actually pretty expensive too, as it turns out, because I did splurge and buy pre-bent wires instead of making them all myself. So I probably spent about $4,000 on this. And somebody asked how many hours have I spent. It's been a long-term project over the last 3 years. It's actually kind of calming. I've likened it to the electronics equivalent of like bonsai tree trimming.
I've got what has been the hardest part of the project?
The hardest part was the assembly. The second hardest part was debugging things. But I have to say, the biggest surprise of the project was how well it's actually worked. I've had friends of mine say that they're amazed that the thing works at all. And I've used it to calculate Mandelbrot sets, pi to 80 decimal places. So this is a real computer that really works. That continues to floor me, that this all comes together. And also that something that fits on my living room wall is something that's routinely done, at the head of a pin right now using today's technology.
Okay, so did you buy special breadboards / are you going to do PCBs in place of the breadboards? We got just about a minute left.
So the breadboards I bought directly from China. It's the only thing I've ever used AliExpress for, and I got these somewhat not commercial ready breadboards, but they all work. They just have some misprints on them. And yes, I do believe that I'm going to do a Spikeputor Mark II on PCBs so that it will have some staying power.
Is it reliable? When I build stuff like this, it seems flaky.
Yeah, that's a very good question. At 3,000 hertz, it is almost reliable. At lower speeds, it's very reliable. And I attribute most of the problems that I'm having to things like bad ground planes and, breadboard connections. So I'm really interested in expanding my electronics knowledge and taking it to the next level on that.
Okay, so there's a ton more questions in the Zoom chat, but we are out of time for this session. So if anybody's got more questions, please take it over to Discord to the channel.